Hi Science 10, today 4.2, as we follow 6 different scientists as we see the ideas about heat and energy evolve over time. And we're going to start with Greek philosopher Empedocles, who you may have heard of these ideas before, thought that all matter was made up of earth, air, fire, and water. And different substances were combinations of those things, and he thought that when you burn an object, fire was released, and this idea was held for a very long time until the 1700s, when the phlogiston theory came up with this idea that when you burn something, it had this fluid inside called phlogiston that flowed out when it burned because they felt that heat released and they had to give it some name. But then the third idea came around, this is number 3 now, was the idea of caloric. And this was the idea that heat or caloric was a massless fluid that all things had, and that it would move from hot things to cold things. And this is where we started the idea of the unit of calories. The amount of the calorie was equivalent to how much it would take for 1 gram of water to go up by 1 degree Celsius. And that much was 1 caloric, or 1 calorie. And that idea led to number 4, Benjamin Thompson, who started looking at that caloric theory of the fact that there was a massless fluid. And he was, don't be confused with Count Rumford, because he was the same guy. Benjamin Thompson was knighted and known as Count Rumford. But anyways, Count Rumford was looking at how that flowing caloric could not have caused the heat that he felt when a cannon was shot. So he said he didn't think there was a substance called like caloric, but he said that heat was equivalent to energy and that there was an energy transformation happening. This led to number 5 guy, Julius Mayer, who was seeing some evidence about Rumford's idea, because he said that when he checked out the blood of people in hot countries, they were carrying more oxygen, redder blood. People in cold countries had not as red of blood because they were using more of their oxygen to stay warm. So this gave him the idea of heat being related to energy, but because he wasn't much of a scientific writer, it was this guy, our last guy, James Joule, who was a good scientific writer, and he is the one that actually got credit for his study on heat, and we ended up, from then on till today, we use the unit for energy, named after him, the joule. So you will hear about joules as a unit for work coming up here, because from now on, when we talk about energy, and specifically work as the ability to do energy, we will use the unit, the joule. So when we look at work, realizing that work is done if there is some force put onto some object and it actually changes its location and there was some movement or displacement of that object. So in our topic today, we're looking at one formula, the formula for work, which is simply the force that's given times the distance that that object moves, or the change in distance. And work will be always in joules, as long as you remember to use the force in the unit newtons and distance in the unit meters. So joules will be newtons times meters. And if you have other units besides that, you'd have to convert them. Now, in the force times distance formula, if you prefer using the triangle for three variables, that's a very easy thing to do. And you just memorize that work goes on top of your triangle and force times distance is written at the bottom. So that means if you're looking for work, you're just going to go force times distance. But if you're looking for example, what force is, you can cover that up and just say that it's work over distance to get force. If you're looking for distance, you can cover that up, and the formula is right there. To get distance, it would be work over force. So I'll review that again. To get work, it would be force times distance. To determine force, it would be work divided by distance, just like the triangle shows. If you had to find distance, cover that up, and the formula shows you that it would be work divided by force. So all three of these versions of this formula can be determined out of this triangle. Okay, unit-wise, work in joules is kilogram meters squared per second squared. And so you can see that working when you realize that a Newton is kilogram meters per second squared. So I just wrote a Newton is kilogram per meter squared, multiply it by the distance, which is multiplying by another meter. And that will show you that joules, the unit of joules, actually breaks down to be kilograms meter squared over second squared. The grasp method, look at what's given in your question, check what is being required as what solution we're looking for, and analyze your problem by doing a formula, finding a solution, and paraphrasing that in an answer. So this is just the way that you can set up any problem in physics to methodically get the answer. Before we do that, I have 7 little examples of figuring out whether something is actually work or not. If you lift a book off a table, yes, it's work because you're giving force and there is some movement in some direction. If you carry a bookcase, you move it, you use force, yes, that's work. If you push against a wall, but you do not move that wall, but you keep pushing, you might be sweating and thinking you're doing a lot of force. But if there is no movement at all, then there is no work. Fourth one, you might say you've done a lot of work studying. However, if you're not moving, no force physically was exerted, then you would consider that not work according to our definition in physics. The fifth one, if you compress a spring, you are moving it, you're using force, so yes, it's work. The sixth one, push a sled, you move that sled, you have to use force, yes, it's work. And the last one, if you move the puck, there was some force involved and it moved, so yes, that would be work. So it's important to know which would qualify as work. And a couple of examples before I leave you to try some is this one that's in your notes. 25 newtons is the force, distance is 1.4 meters, so you write down the formula that you will be using, which is force work will be determined by force times distance, and you multiply the two, and it's just 35 joules as an answer, but remember that because we're finding work, make sure that you record your answer as joules, because work, the unit is joules. For another one with scientific notation, if they're looking here how much work is done, and you have to do force times distance with large numbers like kilonewtons and kilograms, and kilometers, you have to realize which numbers we need here. What we need is the force, but we need it in newtons. So if we're using we're looking at kilonewtons, remember you have to multiply by 1,000 to actually get the number in newtons, so we can use this force. And for the distance, we can't use kilometers, we have to multiply that by 1,000 because we need to use meters for the distance in our formula. So once we've got the meters and the newtons, we can take those numbers and do force times distance with our correct units, and then we can safely say that our answer will be in joules. And you can multiply 1.61 times 1, and the answer will be 10 times, adding up exponents. This is some math that you should have taken, or you can use your calculator to add that up, to multiply those numbers, but it's 1.63 times 10 to the 13 if you add the 8 and the 5. We'll probably pretty much be doing much simpler calculations for work, and that may not be an exponent question that you come across, but I thought I'd show you how to do one. For this one, if you can't pick up something, there's no distance, then you could safely say don't have to do the math because there was no work done if there was no distance. Alrighty, I am leaving you to work on page 10 to 12 in your notes, and you can check back with my answer key on those. Thanks for listening, and we will see you soon for some part 2 on